Our second speaker of today is Professor Sasha Sodin from Poisson and Tel Aviv University. And he'll talk about modification of the moment method and its applications to random matrices. So welcome to speak.
Okay, thank you very much. It's a great honor to speak here today. I've introduced a modification in the title of my talk. In the first part, I will try to tell you about a version of the moment method in which exploits certain combinatorial cancellations, making use of the three-term recurrent relation satisfied by certain orthogonal polynomials. And the idea is definitely not new, but in the recent years, it found some new applications to random matrices, and especially to local eigenvalue statistics. And in the second part of the talk, I'll try to show you one of these applications. Before we start, I'd like to mention that the application of the moment method to local eigenvalue statistics of random matrices goes back to the work of Alexander Soshnikov, and most of subsequent work builds on his ideas, and also that my own work on the subject started in collaboration with the Hartfeld. Okay. So let's start with the usual moment method. We are interested in a measure mu, for example, the distribution of some random variable. Some of the properties of mu can be extracted from its moments, S of n mu, which are just the integrals of the monomials psi to the n with respect to d mu of psi. However, the sequence of monomials psi to the n is not very well conditioned, and it is often beneficial to replace it with a better conditioned basis in the space of polynomials. And one choice which is especially convenient is the sequence of orthogonal polynomials PL of psi with respect to some measure mu infinity, which has to be sufficiently close to the known measure mu. So let me recall that the orthogonal polynomials PL of psi with respect to a measure mu infinity are obtained from the monomials psi to the n by the Gram-Schmidt orthonormalization procedure. So they boast many beautiful properties, but one which is especially important for us today is the three-term recurrent relation psi PL of psi equals AL PL plus 1 of psi plus BL PL of psi plus AL minus 1 PL minus 1 of psi. And in many situations, this recurrent relation determines the measure of infinity uniquely. The fact that the coefficients of PL plus 1 and PL minus 1 differ by shift reflect the normalization of the polynomials. So one example is the Gaussian measure with density 1 over square root of 2 pi e to the minus psi squared over 2. In this case, the orthogonal polynomials satisfy the recurrent relation psi PL of psi equals square root of L plus 1 times PL plus 1 of psi plus square root of L PL minus 1 of psi. And this simple relation can be considered as an equivalent definition of the Gaussian measure. The fact that the middle coefficient, the coefficient of PL is 0, is due to the symmetry of the Gaussian measure about the origin. So as an illustration, let me show you a proof of the central limit theorem for sums of independent random signs. So let xj be independent random plus minus ones, and let Sn be the sum of n of them. So we want to show that the distribution of Sn divided by square root of n converges as n goes to infinity to the Gaussian measure. There are many ways to do it. Of course, one is as follows. Let's consider the expression S of n L, which is the sum over all L tuples of distinct indices j1 up to jl, which go from 1 to n, of the products xj1 times xj2 and so forth up to xjl. It is crucial that the indices are distinct, otherwise this quantity would just be the nth power of Sn, and we would be back to the usual moment method. Okay, so these quantities SNL have two important properties. The first one is that they are orthogonal. If we multiply SNL by SNL prime when L is different from L prime, then the product coming from SNL and the product coming from SNL prime have a different number of terms. Therefore, there should be at least one random sign which appears in one and not in the other, and therefore the expectation of the product should be 0. The second important property is the three-term recurrent relation. Sn times SNL equals Sn L plus 1 plus a combinatorial factor L times N minus L plus 1 times Sn L minus 1. The reason why this is true is that if we take a term xj1 up to j coming from SNL and multiply it by another random sign, there are exactly two possibilities. Either this random sign is distinct from all the L signs which we had, and in this case we get one of the products appearing in Sn L plus 1, or it cancels one of the signs coming from SNL, and in this case we get a term of Sn L minus 1 with exactly this combinatorial factor. So, in particular, these S and L are polynomials of Sn. They're polynomials and they're orthogonal, therefore they should be the orthogonal polynomials with respect to the distribution of Sn. And the only thing which we need to do to avoid the Denis-Sidorian fallacy is to normalize them, which is exactly the same as to symmetrize this recurrent relation. Okay. Let's do that. We consider sigma and L, which are the normalized S and L, and also we'll consider them as polynomials of Sn over square root of n to incorporate the factor of the central limit theorem. And in this case, the recurrent relation term takes the form Sn over square root of n times sigma n L equals A n L sigma n L plus 1 plus A n L minus 1 sigma n L minus 1, where the recurrent coefficient A n L over here is equal to square root of L plus 1 times 1 minus L over n. So all the computation is basically on the screen. So now we can pass to the limit as n goes to infinity. The coefficients obviously tend to the recurrent coefficients of the Gaussian measure, and therefore by standard theory the distribution of Sn over square root of n converges to the Gaussian distribution. So instead of pursuing this line of thought, let's proceed to the to its matrix analog, which is the topic of this talk. So, in the matrix case, the moment method relies on an expression for matrix element of powers of a matrix H in terms of sums of products of matrix element of the original matrix. So, for example, the VW element of H to the fourth is equal to the sum over all triples of indices V1, V2, and V3 of HV, V1, HV1, V2, HV2, V3, HV3W. Now, it's convenient to visualize such triples of indices as paths of length 4, which go from V to V1, then to V2, then to V3, and then to W. And we sum over all possible paths, including paths which attend a certain vertex twice. Now, in the modified moment method, we look for a polynomial P4 of degree 4, so that if we plug in the matrix H and take the VW matrix element, we'll get more or less the same sum, except that certain paths should be excluded. So we want to exclude all paths which backtrack at a certain point, so the picture on the left is not allowed. We're not allowed to return to a vertex from which we just came. So the path on the picture on the left is prohibited, the picture on the right is allowed. Okay, so in this degree 4 case, the condition is that V is not equal to V2, V1 is not equal to V3, and V2 is not equal to W. So since this is a bit vague, let me show you an example. Let's consider a kappa regular graph G, meaning that we have a set V of vertices, and every vertex is connected to kappa other vertices by H's. And then we consider the adjacency matrix of G, which is a matrix whose rows and columns are indexed by the vertices of the graph, and we have a matrix element is 1 if the row and the column are connected by an H, and 0 otherwise. And also let's consider the sequence of polynomials PL of psi defined by the recurrent relation PL plus 1 of psi equals psi PL of psi minus kappa minus 1 PL minus 1 of psi, with the initial conditions P0 equals 1, P1 of psi equals psi, P2 of psi equals kappa psi squared. Now I claim that if we take the adjacency matrix of this arbitrary graph, plug it in the Lth polynomial, and take the VW matrix element, this will count the number of non-backtracking paths of length L from V to W in our graph. So for comparison, if instead of PL we would take the Lth monomial T to the L, this will count all paths of degree L. So the proof goes as follows. Let's consider the matrix TL, the matrix elements of which count non-backtracking paths of length L in the graph. We need to show that these matrices satisfy the same recurrent relation as the polynomials PL, namely TL times T should be equal to TL plus 1 plus kappa minus 1 times TL minus 1. And the proof goes pictorially as follows. Let us take a path of length L which goes from V to VL, and let's denote by VL minus 1 its penultimate vertex. Now we take this path of length L and append to it another H which goes from VL to W. There are exactly two possibilities. Either the penultimate vertex VL minus 1 is distinct from W, and in this case we get a non-backtracking path of length L plus 1, and these are the terms of TL plus 1, or VL minus 1 coincides with W, and in this case we get a non-backtracking path of length L minus 1 with a combinatorial factor kappa minus 1, and this modulus and details is the proof. So this claim can be used to study the properties of a non-backtracking random walk on a graph using the spectrum of the adjacency matrix, but today we will discuss applications in the opposite direction where non-backtracking walks are used to study random matrices. So here's a slide with a list of some applications. So one group of applications deals with extreme eigenvalues close to either the largest one or the smallest one. And in this case, one can obtain rather precise results. One can study local eigenvalue statistics, meaning that we can consider the distribution of the largest eigenvalue or the joint distribution of 15 largest eigenvalues without doing any averaging. However, to be honest, I should admit that in principle these results could probably be reproved by the usual moment method, except that presumably the proofs will become longer and less transparent. So the main question, so another group of questions concerns the bulk, the center of the spectrum, and there the modification of the moment method is really crucial. However, so far no one has succeeded to apply the method to local eigenvalue statistics, such as the distribution of the gap between two adjacent eigenvalues. However, there are important results, mainly due to last layer anti-knowledge, pertaining to intermediate scales or mesoscopic scales, where one averages over a window containing a number of eigenvalues tending to infinity, and the game is to make this window as small as possible. Okay. So in the next part of my talk, I will tell you about one of these applications, about band matrices, but we'll first need an introduction. Let me start with an introduction to the circle of questions. So let's consider the eigenvalues psi1 up to psi n of some kind of random remission matrix Hn. So local eigenvalue statistics are about quantities which depend on eigenvalues near a fixed value of the spectral parameter, which we denote E. So we want to zoom in very closely near E, so that the mean spacing between eigenvalues will become of order 1. And one way to do it is to subtract from all eigenvalues this number E, and to multiply by some scaling factor, which is something like the inverse mean spacing, so that most of the eigenvalues will fly away to infinity, and the ones which are left are the ones which we want to study. So pictorial, here is a pictorial example. I took two random matrices, two different random matrices, and plotted the histogram of eigenvalues. And the histograms look pretty much the same. So the global eigenvalue statistics are identical. However, if we zoom in near 50 and look at the eigenvalues near 50, zoom in so that the mean spacing becomes of order 1, we see that the local eigenvalue statistics are completely different, and in particular, the eigenvalues of the second matrix are much more rigid. Okay, so that's what we see on the right hand of the slide. Will be particularly interested in random matrices with geometric structure. Again, this is a very broad circle of questions. Today I'll focus on the following setting, which is sufficiently rich to incorporate many interesting examples. So again, Gn will be a large graph with n vertices. N is a large number, and we assume that every vertex is connected to kappa and other vertices. And then we construct a random matrix which has independent copies of one random variable on the vertices, and independent copies of another random variable on the edges, and we introduce some kind of normalization factor, for example, 1 over square root of 4 kappa n plus 1 to make the spectrum of order 1. So, two examples. If we take the empty graph, we'll just get a random diagonal matrix with the dependent entries on the diagonal. This can be, of course, studied. And if we take the complete graph, where all pairs of vertices are connected by edges, we get Wigner matrices, which are the classical objects of random matrix theory. So let's focus on these two extremes in some more detail. If we start from a random diagonal matrix, so that the diagonal entries are copies of a random variable with a density rho of psi, and we zoom in near a point E where the density is positive, then the correct normalization factor is n times rho of the density at E. And if we do this rescaling, what we get in the limit, as it then goes to infinity, is what is called the standard Poisson process. What this means is that the probability that the number of points in an interval equals k is proportional to the kth power of the measure of the interval divided by k factorial. And the measure is the Lebesgue measure. Since we started from independent random variables, it's natural to assume that some of this independence is preserved in the limit, and indeed, for example, the point counts in disjoint intervals become in the limit independent random variables. Another feature of the Poisson process is that the variance of the point count in any interval is equal to the expectation. Now, sometimes we'll be interested in points where the density, in the local eigenvalue statistics where the density is not positive. In this case, the scaling is different. However, in the limit we still get a Poisson process, except that this M is no longer the Lebesgue measure, but some other measure called the intensity of the Poisson process. But these two properties, the independence and point counts and the equality between variance and expectation still remain true in the general case. On the other extreme, we have Wigner matrices. In this case, in the limit, we get a completely different family of processes called sometimes random matrix processes. And the points there are much more rigid. In particular, the variance of the point count in a large interval grows as the logarithm of the expected number of points, not linearly the expected number of points. And later I'll show you the definition of one of the processes of this kind. So, under the very mild condition that the connectivity, the degree of the graph tends to infinity with n, the global eigenvalue distribution of the eigenvalues of the matrices which we constructed is given by the semicircle law, meaning that the fraction of eigenvalues in an interval j tends to the integral over j of 2 over pi times square root of minus xi squared. But as we saw in the picture a few slides ago, a priori this tells us nothing about local eigenvalue statistics. It may be arbitrary, it may depend on the graph in an arbitrary way. In view of this, it's quite surprising that there is a conjecture which makes an order in this in some generality, and so it is believed that for quite a general family of graphs, one gets the same behavior as in one of the two extremes which we saw. So the conjecture is as follows. It's due to further urban mirroring, and it is based on early ideas of David Fowler's in the context of the Anderson model. So let's consider the following quantity, m over n of e squared. It's really an important quantity. One way to think about it is as the ratio between the mean spacing between eigenvalues about e and the density of eigenvalues per unit volume in the vicinity of E. Now, the criterion is formulated in terms of the behavior of the random walk on the graph Gn, which starts from some point and goes an squared over n steps. So, and it says the following, that if after n squared over n steps the random walk mixes or equilibrates in the entire graph, then the associated random matrix should have random matrix statistics near E. On the other hand, if after this number of steps the random walk remains localized in a small subgraph of the graph, then in the limit we should get some kind of Poisson process. I would like to emphasize that, at least to my taste, the challenge here is not to prove or disprove this conjecture in maximal generality, but to understand the behavior, at least for some simple examples. Okay, so in many cases, for many graphs, there is a simple quantity called the mixing time, which controls the mixing of random walk. So it is such that when you're below the mixing time, the random walk is localized in a small subgraph, and if you're above the mixing time, then you're essentially mixed. And in this case, the criterion can be restated as follows. If the mixing time is much smaller than the quantity n squared over n, we should get a random matrix process, and if it's much larger, we should get a Poisson process. So let's consider the following example, which is both one of the simplest non-trivial examples where this conjecture can be applied, and also it's important by itself in view of some physical application. So the graph, the vertices of the graph will be labeled by residues modulo n, and we connect two vertices if their difference modulo n is less than some parameter which is called the bandwidth, which we denote W of n. So here I drew a graph corresponding to size 7 and bandwidth equal to 2. So one can compute, in this case, one can compute the mixing time. It's up to constants, it grows as n squared divided by w squared. And since we have n eigenvalues and the spectrum is normalized to be of order 1, we expect the mean spacing to be between eigenvalues to be of order 1 over n. And therefore, the quantity n squared over n should be of order n, and if we believe in the Federer-Mirlin conjecture, we should expect that when w is much greater than when the bandwidth is much greater than the square root of the matrix size, in the limit we should get one of the random matrix processes, and if the bandwidth is much smaller than the square root of the matrix size, we should get a Poisson process. This conjecture is supported by extensive evidence. In particular, there is a very convincing derivation by Federer and Mirlin based on the supersymmetric formalism. However, for now, no one managed to put any of these arguments on anywhere close to a mathematical justification. However, there is one case where the counterpart of this conjecture can be rigorously checked, and these are the spectral ages, and this is what I would like to tell you now. But first, let me formally define the limiting process for the case of Wigner matrices. So the definition is a bit cumbersome, especially if you haven't seen it before. So to define the limit, so the limiting object is a random decreasing sequence of numbers, lambda 1, lambda 2, and so forth. And to define it, it's defined in terms of the correlation function, which are the sums of the probability density, joint probability densities of all k tuples sampled from this sequence. And this k correlation function is given by a k by k determinant, and the kernel of the determinant is expressed in terms of the Airy function, which I drew in the picture on the right-hand side. So I assume it's quite scary if you haven't seen it before, but I also won't use it. I just wanted to have it on the slide. So with the normalization, if we take the eigenvalues, scale them near 1, which is the right edge of the spectrum, and multiply by 2n to the 2/3, then in the Wigner case, you get in the limit this Airy 2-point process. This was first proved for a special case of random matrices called the Gaussian unitary ensemble by Forrester and Tracy Widom in the early 90s, and it took a while until a general limit theorem was established, first by Sochnikov under some assumptions, and then recently by Li and Yin under minimal conditions of the entries. So here is the picture of the first correlation function of the Airy process. The reason why I plotted it is that it looks, as we expected, it looks similar to the right edge of the semicircle, which is not surprising, and so it's approximately equal to 1 over pi times the square root of minus x. And to the right hand of 0, the positive axis, it decays very fast. So it's returning to the comparison between Poisson and random matrix process, we can compare the Airy 2 process with the Poisson process with this intensity. And they have, by construction, they have more or less the same expected number of points in a large interval, which grows like t to the 3 over 2. However, the Airy 2 process is much more rigid. For the Poisson process, the variance is equal to the expectation. For the Airy 2 process, it grows logarithmically in the expectation, as we discussed before. And now I can say the result. So first, this is the most important part, that if the band for band matrices in the limit we get an Airy2 process if and only if the bandwidth grows faster than n to the power 5/6. To relate this to the further equivalent criterion, we need to compute the average, the mean spacing between eigenvalues at h, which is also not so obvious, since only in the regime when W is greater than n to the 5/6, it is equal to what would be predicted by the semicircle, otherwise we get a different answer. And we can plug it into the criterion, and indeed the criterion is confirmed. So at least to my understanding, this gives one example where the further criterion can be rigorously verified. Okay. So in the last part of the talk, I'll try to show you some ideas on the proof. In particular, I'd like to explain where the mixing, how the mixing time comes in. So I'll show you the argument for one direction, that if the bandwidth grows faster than n to the power 5/6, then in the limit we get an Airy2 process. The argument consists of 3 steps. The first step is where the modified moment method is applied. I will only tell you the conclusion. The conclusion is that what we need to do is to count k-tuples of closed non-backtracking paths. Closed means they start at the same place where they end in this graph Gn, such that every edge is traversed the same number of times in one direction as in the opposite direction. And the symptotic regime in which you will be interested is when the number of paths is fixed and the length of the paths are of order n to one third. And this n to the 1/3 is very important. So here is an example of such 2 paths. So these are 2 paths, each one is of length 9, and we see that indeed every edge appears once in one direction. Here we have 2, 8, and here we have 8, 2, here we have 5, 6, and here we have 6, 5. So every edge is traversed once in one direction and once in the opposite direction. Okay. Now we need to enumerate them. So the second step is to divide all such k paths into equivalence classes, and I will only work with this particular 2 paths, so I'll show you how to construct each equivalence class. So the first thing we need to do is to draw the 2 paths. So here the first path, which goes from 4 to 2 to 8, 1, 5, 6, 7, 8 to 4. And here the second one, which goes from 3 to 9 to 5, 1, 8, 7, 6, 5, 9, 3. Okay. Then we erase all the labels, and the picture which remains is basically our equivalence class. So there are infinitely many equivalence classes. I won't draw all of them, but I drew one more complicated one just to show how they look. Okay. And now comes the third step, in which we need to count how much every equivalence class contributes. And here our goal is to show that if the mixing time, which is n squared over w squared, is much smaller than n to the 1/3, then the contribution is asymptotically the same as for the complete graph. So we need to show that the bandwidth, that in this regime the bandwidth enters only as a trivial scaling parameter, and then since we already have the result for the complete graph for Wigner matrices, we obtain it by extension to for band matrices. So again, I'll only work with this particular equivalence class from the previous slide. So we need to count how many ways are there to embed this picture on the top into our graph GN. So let's denote by L1 and L2 the length of the two paths, and let's denote by M1, M2, M3, and M4 the length of these four pieces. So for the pair, which was 2 slides ago, the length are 2 and 3, and as we would expect, 2 plus 2 plus 3 plus 2 is 9, and 2 plus 2 plus 3 plus 2 is also 9. Okay, so L1 and L2 are L1 and L2 are L1 and L2 are given. They are of order n to the 1/3, and now these numbers M1, M2, M3, and M4 have to satisfy the length of the pieces of the path have to add up to the length of the path. Show it here. So the first path goes like this. It goes over this piece, and then it makes this circle and returns. So we have to so M1, M2, and M3 have to satisfy twice M1 plus M2 plus M3 equals L1. And similarly, M4 plus M2 plus M3 plus M4 should be equal to L2. And now, since L1 and L2 are of order n to the 1/3, and these are chosen from the set of solutions to the sequence of equations, typically all these pieces are also of size n to the 1, typically also of size n to the 1/3. And now we can more or less conclude the proof. So now we need to count the number of the number of embeddings of this into our graph. So what we do? We start from an arbitrary point in the graph. There are n vertices in the graph, so there are n possibilities. Then we start a random walk. Where we can go anywhere in the first stage, second stage, and so forth. We do M1 steps, and on every step we have 2W or maybe 2W plus or minus 1 possibilities for this. So we get a factor 2W to the M1. Then we go here, we get another combinatorial factor 2W to the M2, and here we get another factor 2W to the M3. And now, and this is the punchline, we have to multiply all this by the probability that after these M2 plus M3 steps, we return to the same, to this very vertex. But since we assumed that Mj are of order n to the 1/3, which is much greater than the mixing time, the probability to arrive at any fixed vertex, in particular the one where we started, is asymptotically 1 over n. And we see that this 1 over n cancels this n. Well, and then we need to multiply by the number of possibilities to glue this tail on the right, which is 2W to the M4. So after we have done all this, we got an answer in which, indeed, as I promised, the bandwidth W enters only as a trivial scaling parameter. Therefore, the answer doesn't depend. Therefore, the answer doesn't depend on W, and this concludes the proof. So here are the main steps of the argument. First, the moment method, the modified moment method, reduces the equation to counting capable of non-backtracking paths of length n to the 1/3. This is related to some methods of physical perturbation theory, self-energy generalization, or coherent potential approximation. Then we classify such capables of paths according to their topology. The pictures which I drew at some point are related to ribbon graphs, and this is also related to the genus expansion introduced by 't Hooft. And then, for every equivalence class, we compute the number of k-tuples of paths which correspond to it. And we see that if the size of the path is if n to the 1/3 is much greater than the mixing time, the bandwidth enters in the answer was only the trivial scaling factor, and therefore the answer should be the same as for the complete graph that is the Airy process. I think I've told you everything I wanted, so let me stop here. Thank you very much.
Are there any questions? Okay.
So you can try the unmodified monoidal method for these problems. Why did you?
Because then we would have to consider non-backtracking paths, twice non, that is paths which may be backtracking of length n to the 2/3 rather than n to the 1/3, and therefore the role of the mixing time would not be so obvious, so you wouldn't see the appearance of this condition. So indeed, presumably one could adjust it with, and I believe that this problem, unlike some problems pertaining to the middle of the spectrum, could be solved by the moment method, but it would be much less, it would be less transparent. You wouldn't see that.
So about the mixing time of the graph, can you tell me more about it? Like asymptotics, for example, number of vertices or edges.
For which graph, once again?
And for for example, any random regular K graph like you mentioned, or
so.
Can you please go up to previous slides?
Okay.
Like 1 year in the beginning.
More?
Like one around the beginning. Can you further? Oh yes, that's like the slide next to it.
Pardon? Once again.
The slide next slide.
Next.
Oh yeah.
Okay.
So I was wondering what the asymptotics of T-mix.
So for these particular graphs, it's very easy to compute because the graph has symmetry, so you can diagonalize the adjacency matrix and in Fourier space. So it's easy to compute. You can compute it precisely. You can write a formula for it.
And for example, what would happen to random graphs?
No, for random graphs, everything is easier since the mixing time is of order 1, so you always have random matrix statistics. So this is known. For the matrix, the random matrix associated with the random regular graph is will always be even for a 3 regular graph which has a random matrix statistics.
Okay, thank you.
Okay, so let's thank our speaker again. So.